Wow, pre-calculites, can you believe we're already here in section 7? Let's call this lucky number 7. This section could be called the whole reason you learn algebra and they put the variables and letters in with your numbers. It's so that you can find formulas, make predictions, make projections, find out how much money you're going to earn if the trend continues. The whole reason that you learn mathematics is to be able to make a model and solve problems. So that's what we're talking about today. So let's look at your note. A square of side x inches is cut out of each corner of a piece of cardboard. They're going to fold up the sides to make an open-topped box. And we want to know what the maximum value would be. So we're going to write a volume as a function of x. We're going to find the domain. Now, the domain for this problem is different than the domain would be for the function. Because in real life, you cannot have a negative volume. You cannot have a negative length. So we're going to have to reflect that in the domain. So sometimes your book will talk about what's the domain for this problem situation. That means in the real world, where you can't have negative length or width or area or volume, it all has to be positive. What would be the domain? And then they'll also say sometimes, what's the domain for the function? And that's different. You got to take into account, in theory, the whole function. Then we're going to graph the function. Use the max and min finder on your graphing calculator to determine the maximum volume that the box can hold. And how big, this is the final big kahuna. How big should the cutout squares be in order to produce the box of maximum volume? We want it to hold the most. So let's take a look. Here's the picture. And what they're doing is they're cutting out these little squares here on the four corners. They're going to fold it up to make a box. So if they're cutting out a square of length x, that means from here to here is x, and from here to here is x. Now they like to put this on standardized tests. A lot of people forget that even though we're starting out with an 8 by 15, this length would be 15 up and down, right there. But we're cutting an x out here and an x out here. So the length of our box when we fold up the sides is going to be 15 minus 2x. Standardized tests, people forget to subtract 2x. They only subtract 1. But you'll know better. Then the width down here, they said it was 8 inches by 15, so it was 8 inches to start with. We're going to subtract x from both sides, so we get 8 minus 2x. And then the height of our box is going to be x. Hopefully by this stage of the game, you know that the volume for a box is length times width times height. So we're going to multiply these three things together. X, 8 minus 2x, 15 minus 2x, that's going to give us the volume. Now, we already said that the length cannot be negative. Well, we know x has to be positive, but this has to be positive as well, and this has to be positive as well. If we find this one, it should take care of our problem. So, we can't have a negative length or volume, so when we're looking at the domain for the problem, we're going to take that into account. X has to be bigger than 0, and x minus 2x has to be bigger than 0. So we're going to solve that for x. X minus 2x greater than 0, minus 2x from both sides. Remember, if we divide both by a negative, we got to flip the old inequality. So we end up with x less than 4. Negative over a negative is a positive. So we know it's got to be greater than 0 and less than 4. Now we could solve this one here, but you know you're going to get x less than 7.5, and all three of these have to be satisfied, so that's why we're just going to stick with this x less than 4. So the depth of x must be non-negative, as must the side length and width. The domain is going to be 0 to 4, so we should have said less than or equal to here and here, but you can handle it, because you could have a length of 0, but you wouldn't have a box. Domain is 0 to 4, where the endpoints give a box with no volume. Volume. So that's our domain. Why do we care about our domain? Because it's going to help us find our max and min on our graphing calculator. So if we look here, we're going to graph this guy. And what we're going to do is we're going to put y1 equals x times the quantity x minus 2x times the quantity 15 minus 2x. So if we graph that in there, we're going to get this picture of our graph. Now, the question becomes, how do you find the y, though, the y min and the y max? What I would do is go to the table and look what happens between the x values of 0 and 4, about how high does it go. If you look at your graphing calculator, you're going to see it goes about 88 in there is the max volume. I just give myself a little cushion room in between there. So then to find the maximum, Remember, you go second, and then you hit the trace button, takes you to the calculate menu. Then you calculate the maximum, select maximum, arrow to the left and enter, arrow to the right and enter a third time, and it'll give you this maximum. At this point, you need to recall, what does X stand for? And what does Y stand for? What does Y represent? What does X represent? If you don't know that, you still can't solve the problem. So some people like to write what X represents in words at the beginning of the problem. I just say, well, Y equals, this was Y1 equals this whole thing. That represents volume. So the Y is the volume, and if you look at your picture, the X represents the amount you're cutting out. So the maximum occurs at 5/3. 5/3 is 1.6666666, repeating, comma, 90.74. That's our volume. So the maximum volume is about 90.74 cubic inches. Remember, cubes for volume, because you're looking at how many little cubes would fit in there. So here's our solution, how we would write it up. A square of side x inches is cut out of each. How big should the cutout squares be? Each square should have sides of 1 2/3 inches. That's going to yield the maximum volume holding box. Alrighty, let's look at this next one. We got grain leaking out of a storage bin at a rate of 5 cubic inches per minute. The grain forms a cone-shaped pile on the ground below. As it grows, the height equals the radius. If the cone is 1 foot tall now, how tall will it be in 1 hour? First off, I want you to notice that the volume is in cubic inches. And I know this is the volume because this is a volume measurement because it's got cubic inches. Now it's a volume per minute, so we got to kind of take that into account. Cone is 1 foot tall. 1 foot, inches. So we might have to do a conversion later. So already my wheels are spinning. So volume of a cone, just in case you don't remember, it's 1/3 pi r squared h. 1/3 pi times radius squared times the height. Since the height is equal to the radius, we can actually replace this r squared with h squared because the height and the radius are going to be equivalent, which helps our calculations. So this volume is going to become 1/3 times pi times h cubed. So when h is 12 inches, now where did they get to 12 inches? Because it said it's 1 foot tall now, if you look at the problem. So we're going to substitute 12 in for the h. So volume is going to be 1/3 pi times 12 cubed. That gives us 576 cubic inches, and I like to leave the pi in there because sometimes when you're doing these kind of problems, the pi's will cancel out. Sometimes they don't, but leave it until the end. That way your approximate answer is the most accurate approximate answer you can get. An hour later, how tall is it? Well, how many minutes in an hour? There's 60. So an hour later, the volume is going to grow by 60 minutes times, it's 5 cubic inches a minute. If we multiply those together, we end up with 300 cubic inches. That's the new volume. Then we're going to work backwards to find what the new height would be. So the total volume is going to be 576 pi plus 300 cubic inches. And that's going to we're going to set that equal to the volume to find the height. And notice I just leave that the same. So the question is, how do you solve this equation? The hard part is done. The hard part is getting to the equation. So we're going to multiply both sides by 3 in order to get rid of the 1/3. And we're going to have to divide by pi in order to get rid of the pi on this side. So this is where they get this. H cubed equals 3, that took care of the 1/3, times the quantity 576 pi plus 300. Then we're dividing off the pi so that we get h cubed by itself. All right, how do you get rid of a cube? You root it. So the opposite of cubing is cube rooting. So h is going to be the cube root of this whole shebang. You plug it in your calculator, make sure that you divide everything, you multiply everything with order of operations. I would probably put it all in there with the parentheses. Notice if we hadn't had the 300 down here, the pi's might have canceled out. Had you converted to a decimal, you'd get an ugly answer, you know. So I'm just saying. All right, we end up with approximately 12.63 inches. So that's how tall it would be. Looking at scatter plots and data. Now this is the way that most businesses work. They get a bunch of data and they say, what's the pattern? What should our budget be? How much should we sell this for? So this is where this regression analysis comes in. These steps are in your book. You're going to make a scatter plot, look at the shape of the plot, and determine which regression is the best. And then you're going to transform a basic function of that type to fit the points as closely as possible. So this is on your notes here, and we're going to input. Remember, this goes into L1. This is our X, and this is our Y. We're also going to look at this data to set up our window, our max and our min. X min, X max. Now, if we're trying to make a projection, we want to leave a little bit of wiggle room in there. Y min, Y max, same thing. We want to leave a little bit of wiggle room. So we're going to look at both the linear and quadratic regression model for the data. Linear means it's a line. Quadratic means it is a parabola. And we're going to see which one follows the data along a little bit better. So we're looking at the TI-83 Plus right now. You're going to input your data. You go hit the Stat button and then select Edit. That'll come up. You hit number 1 or Edit and then put in your data. So here's our X's, here's our Y. After we put those in, we go to second and Y equal to turn on our stat plot. Sometimes the plot's already on, but we like to double check. So second and then Y equals brings up this. Notice mine's already turned on and I have the correct type selected, and it's going to pull my X's from L1 and my Y's from L2, and there's what the marker looks like. I'm happy with all that, but if I'm not, I just hit enter and I'll go in here and change everything. Window needs to be set to fit the data, so click the window button, and I'm going to do X min is 1990 because that's my little lower than my lowest, and Y X max to be 2010 because it's a little higher than my highest. Y min 180, Y max 400. I also set the scale to 0, the Y scale to 0 here, so that I don't get all those little marks along the Y axis. When I do that, I'm going to go ahead and actually hit graph. And there's what your scatter plot should look like on your calculator. So then we're going to do the linear regression part and see how close we can get. So linear regression, you go to Stat, Calc 4. So we're going to hit Stat, Calc, and hit the number 4. That'll bring up your linear regression. It looks a little different on the TI-84, but you follow along and do about the same thing. So we're going to have to put L1, L2, Y1. And I like to put the Y1 because it plugs it into the Y equals portion of our calculator. So L1, L2, to get that you do second, number 1, second, the number 2, Then to get the Y1, you go to vars and hit 1, 1. So if we go to vars, we arrow to Y vars and hit number 1 and then hit number 1. Forgot the Y vars thing in there. Now, on the TI-84, you put the Y1 after the store reg equation. So, but for our instances, all we're going to have to do now is hit enter, and then you can kind of look at the graph. But I like to hit enter, and I actually like to go to Y1 and make sure that that equation went into my Y1 for me. And that's why we put that comma Y1 in there, is so that it would go right in. Now if we look at my graph, it looks pretty good. It hits 1, 2 points. It looks like a pretty good model. Let's see how the quadratic one compares. So we're going to go ahead and do, this should say quadratic regression. We're going to do Stat Calc 5. And there is calculate number 5. Second 1, 1, we put in all our Y vars, but this time I put a Y2 in there so that I can compare both of them, and it'll put the second equation in the Y2. Hit enter, and then you can look at the graph of it. So there's the graph. And it's kind of hard to tell, isn't it, what's going on? I can't tell which is which. So what I did is I went back to Y equals, and I went to the equals and hit enter so that it wouldn't show the line graph. So now when I look at it, that's what it looks like. To me, that's a better approximation of our data because it kind of dips it a little bit closer to these guys right here. So I would say that the quadratic is the best model. And that's what they say as well. So here's the two models, linear regression and the quadratic regression. The quadratic regression appears to model the data a little bit better than the linear regression equation. Okay, now in the back of your sheet, I put all the functions, and I will talk about this a little bit in class about how they're all applied to different things. I think it's a good thing to have. It's a good reference for you to have. I'll see you tomorrow.